So this is the problem here, the lamp filament. Let's say this is the lamp here and this is the lamp here. So this is called the short shunt connection and this is the long shunt connection. It's sometimes called, the short shunt is sometimes called low resistance method and the long shunt is sometimes called high resistance method. So basically this is the difference in the connection is just like this. So the voltmeter is connected in short shunt directly across the element and ammeter is connected outside these two. So what happens as a result, the ammeter reading is given, which is, let's say, the meter reading, so let's call it IM, and then you have the voltmeter reading, which is 120 volts, which is right across the element here. And but this current IM, because the voltmeter doesn't have an infinite resistance, this current will not entirely go through the filament. Some of the current will be shunted here through the voltmeter. So how much, that we know if we say IM is the total current, meter current, sorry, IM is the total meter current. Let's say IM, and then that is equal to the filament, the what's that thing, filament, lamp filament current. So that's given X here. I will just write maybe X plus this one is the volt current through the voltmeter. So let's call that IV. Now this one is given 0.125. This is the current we need, IX. And this one will be 120 divided by the resistance of the voltmeter. So we can see that Ix is less than that, 125, and this one 120 divided by 1500 is 0.08, so that's 0.08. So this is 0.045. Now I doubt the data here in the problem because the voltmeter resistance shouldn't be this low. This is very low actually. It shouldn't be this low. This low a voltmeter cannot be used to measure such a resistance. So the resistance from the meter we get, I have calculated this first, but let's first calculate the resistance from the meter. That is just 120 divided by 1.125 because this is the voltmeter reading, the reading of the voltmeter, voltage by voltmeter, and this is the voltage by ammeter. I previously wrote IM, so I don't know, I will just write IA, sorry, voltage by voltmeter divided by current by ammeter. So if I say just IA, just from the meter, so maybe we can say IVM and IM, I don't know, and that gives us 960 ohms, while this one Ix is 0.05. So the resistance, actual resistance will be, voltage is voltmeter voltage, but current will be Ix because that is the current that goes through the filament. This is the voltage which is across the filament. So Vm and Vx will be the same. Vm and Vx in this kind of connection will be the same. So that is there. But the current Ix we needed to calculate, and we have calculated that to be significantly smaller than this meter current because this resistance is not high enough. As a result, this current is significantly high and this current is less, much less. This is a bigger current than this one, which it shouldn't be at all. So I really doubt the data here. This one should have been higher because this is a crazy way of this shouldn't be. So anyway, from this data that we have here, that will be the resistance, actual resistance, and which is 2666.67 ohms. So you can see the difference, it's huge. So that's the real one, 0.67 minus 960. The percentage of error is huge, 0.67 into 100. So that's almost 64%, which is, it's impractical. So that's there, but I will just do it as the data. And also the current here is given only for the short shunt ammeter. it's not given for this one. What is the reading here? It is not given, and also the voltmeter reading is not given here, so that's a bit of a confusion. We can't do it properly, but what I can do here, what I will tell, at least theoretically, what happens here is Vm, the voltage here, the current through the Ix is the current through the meter. That's right. So it doesn't change. So I meter is equal to Ix. That is the meter reading. But the voltage here will be the voltage drop across the emitter. Um, if I just write the emitter and then plus Vx, that is there. So this is 120, and meter voltage will be, we know the meter resistance, ammeter resistance, which is, I guess, it's given, of course, 0.08. So that's there. 0.08 is the meter resistance, and the meter current, if it is 0.125, again let's assume that what it is. So this is the ammeter current, which is meter reading, but this one says here that the short shunt diameter is this one. If the for the long shunt it is the same current, let's assume so, then the voltage drop here will be, because this is the current, 0.125 times this resistance. So that voltage plus this voltage will be this one. So now we have to calculate what is the accurate Vx. So Vx will be now 120 minus 0.125 into 0.08. So that's becoming 0.1, which is good. It's more possible result. So 119 volt is the actual voltage drop. So that is what we get now, and so the actual resistance Rx, if we say, that's what it's there. So Vx over Ix. Now here Vx is what we calculated, while Ix will be the meter value, which is 0.125, and Vx is 119.9. That gives us 959.2 volts. So this is a much realistic result. So this is the real, sorry, not volt, it should be ohms. So this is the real resistance, while the error was 960. So that's 959.2 minus 960 divided by 959.2. That will be the error, and you can see that the error here percentage will be negative. So it's probably 0.083, very small error. I hope this is correct, but just double check the calculation, because this part is very small, and then anyway like that. So this is a very small error, and that's what you expect when you do a measurement. You cannot expect to have, I mean, if you get this kind of result, that means you change the meter, otherwise it doesn't make sense. So basically for this problem, because we can see the ammeter, we can see, and it makes sense, we can see the filament resistance is, from the meter it's 960. Now if we use a voltmeter that has just 1500 ohms resistance, which is very close to this value, we have seen previously that we have talked, even the previous video, I tried to say that the voltmeter resistance should be few orders higher than this one. So that should be like, if this is 960, that should be probably like, you know, nearly 50k or something to have a good, because this is almost 1k, so that should be like 100k or something to have a reasonable result. But this is almost so if this is almost 1k and that is 1.5k, that's almost the same. So it doesn't make sense. That's why we get such a huge error. So yeah, hopefully you can get how to do this kind of things. So again, once again, quickly reviewing that when you have a short shunt connection, the voltmeter is giving the accurate result, but the ammeter is giving the current, because this is why it's very important to draw the circuit. These kind of problems, everything should come with a circuit. In electrical engineering, everything should come with a circuit diagram. So anyway, this is very obvious now that the current here, that is the meter's current, goes through this one, the filament, as well as the voltmeter. So you have to calculate analytically what is the exact current that the filament is taking, and that's what we have done here using this resistance. So that's for short shunt or low resistance method case, and this is for long shunt or high resistance method case, where the voltmeter is connected like this. So it gives the voltage drop of the filament as well as the ammeter, and here the ammeter is giving the right amount of current that is going through the filament. So that's perfect there for here in the long shunt case. Ammeter is reading right, but the voltage is, this is the reading of the voltmeter, which is 120 volts, that is giving the ammeter reading. This is Vm, which is actually the ammeter. I shouldn't have used M probably because both are meters, maybe A, but just remember that this is the ammeter reading and this is the filament reading. But we need to find the filament reading because that's what will give the resistance when divided by the current. So the ammeter reading we have found like that, the voltmeter voltage drop across the ammeter, and then we have found Vx. So every time it will be Vx over Ix, but for when it is long shunt, we can see that the Vx is not correct from the meter, and when it is short shunt, the Ix is not correct from the meter, but the Vx is correct from the meter. So yeah, hopefully that helps.